Hello, it's Keith here, and this is day 4 of Grime 6502. Now, if you've been following the series, you know that the game is almost playable now. We had the player able to move around, but there was no Grime on the screen. So what's been happening over the last 24 hours? Well, let me update you. First, let's close all these little windows here, because they're just here for the title card of the video. Now, one thing that hasn't happened is there isn't a proper title screen yet, because to pause on that screen, I've had to put an infinite loop in. So let's just take that out, or we won't be able to play anything. And let's have a quick look at the game. So let's start with the 5200 Atari here. And hopefully you can hear we now have some sound. So this is what I call the chibi sound driver, which is a very simple sound driver that just bleeps and distortion noises. It's based exactly on the Z80 before. It takes the same input and it's programmed. There's a different version for every system I use, but it works in roughly the same way in all the systems, which is how I can make a game on this many platforms have sound very quickly. So all I did was I switched it on because I'd already pre-programmed it for this series, and there was a few bugs in it again on various systems, but generally it works okay. So, well, what are you actually seeing here? Well, you can see the Grime is basically working now. The seekers are seeking towards the player. What can't happen though is the player can't die. There also isn't any score. So this is kind of pre-warning of what needs to be done tomorrow. I need to get the title screen working, the score working, the lives working, and the game over screen working. But let's have a look at the other versions of the game, and we'll see what else is going on. Now, at one point, I was having some problems with the Atari 800 version because, unfortunately, the Atari 800 cartridges seem to have a limit of 8 kilobytes, which seems very, very small. And the game at one point was bigger than that, but it seems that the code that was making it bigger was actually unnecessary. So it does seem to be working at the moment, but I might have a problem later on because I don't think there's any way of making a 16 kilobyte cartridge, even with bank switching or anything. So I can probably get Grime down to 8 kilobytes, to be honest, one way or another, even if it means turning off the title screen or something. But it does bode badly for my ability to develop for the platform long term, because 8 kilobytes is nothing. I'm kind of aiming for a target size of 32 kilobytes for my future mini games, bigger than Grime but smaller than Chibi Akuma's. So I'm not sure what I can do with 8 kilobytes. But anyway, as you can see, it works exactly the same. It looks pretty good. So the Apple II now. Now, another thing you might notice is we do have basic animation in place. It's not animating automatically. There is some kind of graphical glitching, which I think is relating to that animation on here. I obviously haven't fixed that yet. But the game code is working, and you can hear the sound is playing as well. Playing very loud. Anyway, so that works. Well, except for those graphical glitches. The BBC version. So here we go, and you can see the BBC version is very, very fast now. I really need to put a delay in it, and I'll tell you why the BBC version is suddenly very fast in just a moment. And now the Commodore 64. So why is the BBC version suddenly very fast? Well, the answer is simple. The Commodore 64 version was very, very slow. It was about a third of the speed of what you're seeing here. I mean, here's looks okay, but what you were seeing before was horrible, horrible, horrible speed. And I was a bit confused because, like, well, the BBC and the C64 are basically using the same graphics routines. Why is the BBC about twice the speed of the C64? And then when I looked at the specifications of the machines, it became very apparent. Well, the C64 has got a 1 megahertz processor, and the BBC's got a 2 megahertz processor, so it's literally twice the speed. And this was what I've been spending a lot of the time on over the last 24 hours. The porting of the Grime code to get the Grime working and the game playable didn't take very long. It took only an hour or two, but I actually then had to reprogram the code because I'm using those sort of Z80 emulation kind of commands to quickly convert the code. It's not efficient, and that was really killing the poor 1 megahertz Commodore 64. I should have died now by rights because I'm surrounded, but as I say, I haven't put in the death code yet. But anyway, you can see it's mostly playable. It's still a bit slow, but hopefully I'll be able to squeeze some more speed out of it. But anyway, let's carry on. The Atari Lynx with its tiny, tiny screen. But you can see it works fine. A bit clearer the animation there as well. Let's say the animation is working on all of them except the Apple II, which is glitching. Probably because I'm having to use 2 different versions of each sprite. Not quite sure where the bug is though. The NES still has speed problems. Now you can see the game's speed is very good. However, the animation up the screen updates are very poor, and this is because I'm using that. I'm updating the screen during that VBlank non-manageable interrupt. The problem with that is there's not enough time to update the whole screen, so I'm only updating about a quarter of it. So that's why you're getting a very slow frame rate. What I think I need to do is alter that NMIA interrupt routine so that rather than updating the whole screen, it just updates the bytes that have changed. This is going to mean reprogramming it again. In some cases it would actually be worse, but I think for this game it's going to make things faster because obviously what's working here is looking very poor, but the NES should be able to do really fast frame rates for this kind of work. So need another rethink on that and another recoding of that game engine, but I'm going to leave that for now. My next priority is get the game fully working and then start tweaking the individual platforms to try and make it a bit better. PC Engine. So fast we can't even see the title screen. And this has actually got a delay. I've actually put a delay in place on the PC Engine now just to slow it down enough to be playable. So this is even after it's been heavily slowed down. But you can see it looks great, plays well. Very nice. Super Nintendo. There's still a graphical glitch there, as I've said before. Could do with a better graphics engine for the Super Nintendo because I'm not waiting for VBlank, which means probably some glitches, but to be honest it's not a priority because the game is running really fast on the Super Nintendo even with this relatively crude routine, so we'll worry about that later or not at all depending on if I run out of time or not, but generally it's okay. And finally the VIC-20. Very strange, the VIC-20 is really fast compared to the Commodore 64, which is really slow, and my understanding is the VIC-20 was the predecessor to the Commodore 64, so very surprising there. I mean, it's all down to the graphical routines are so simple on the VIC-20, but it seems very ironic that the earlier system is vastly faster than the later one. Anyway, I mean, you can see it works fine. It looks quite nice as well. So the VIC-20's been a pleasant surprise throughout this project because I didn't expect the game to be any good if playable at all. It actually looks like it's the Atari 800 that's struggling at the moment because of the 8K limit. Anyway, so that's the state of the game to date. So what I thought it'd be quite interesting to do now is if I go over a chunk of the code, we're going to have a look at the repaint screen command. And on the left here, I've got the current code base. And on the right, I've got the code base as it was yesterday before I did any optimization. So I thought you might be interested in hearing the optimizations that I've made to make the Commodore 64 version as playable as it currently is, because as I say, it was about a third of the speed originally. So most of the optimizations have come down to essentially using the 6502 registers rather than those zero-page fake registers that I've been using, the fake Z80 ones, and of course they appear as a Z_H, whereas the real registers are A, X and Y. So you can see here for starters, I'm now using IXH and IXL instead of HL. The reason for that is my graphics routines don't use IXH and IXL, so I don't need to worry about them getting changed during the graphics routines, which means I don't need to push and pop them. So that's the first thing I've done here, but otherwise this code's basically the same, except I'm now going from right to left rather than the left to right. The reason for that is I'm using the X and Y registers, and you can check when they get to 0, so by going in the other direction I've got an easy way of checking when I've completed things. So that's another optimization I've made. Now you can see here I'm loading IXL, which used to be L, into X here, and we're using it again here later. And really a lot of this, I should just explain, comes down to what I'm doing down here. Now if you look at the original code here, I had a find tile command here, and that find tile command has now been unwrapped and is effectively all of this code here, or pretty much all of it anyway. So I'm no longer doing a jump, I'm now using this optimized version here because it's much simpler. And then rather than doing a find tile for every single tile, I'm only doing one find tile for every single line, and then because the lines are consecutive in order, I'm using the Y register as an offset to that position. Also, rather than adding 768 every time I do a tile, I'm adding that 768 effectively here, because 768 is hexadecimal 300. So I'm adding 3 to the high byte and doing nothing to the low byte, which is the same thing. And then, rather than constantly recalculate DE, I can just do HL, which is my new tile map, DE, which is my old tile map, and the Y register, which I'm constantly incrementing with every row, or constantly decrementing with every row, sorry, is doing all the work of changing the addresses that I'm comparing. Also, rather than doing a push of A and a pop of A here to back up the red in value, I'm transferring it to the X register, which is faster, and transferring it back here. You can see here I used to be pushing and popping HL and BC. I'm no longer doing that now. I'm now pushing only HL, and because I now need to back up DE as well, but I could back that up, but I'm actually recalculating it. I'm just adding hexadecimal 300 here, just like I did up here, to recalculate it so there's less push pops there. And again, I've unwrapped this because I can make it more efficient than these generic ones, because I know things about the structure of the memory that allow me to be a bit more efficient. Now here, instead of doing inks, I'm doing dex, and then I'm seeing if I've gone over 0 here by checking if the value is still plus. If it's not plus, we've gone negative, and we're done. So then we're repeating out. So effectively, this is the inner loop across the horizontal lines, and then this is the Y loop doing each vertical line. And we're still having to use C here because we don't have enough registers, because we only have X, Y, and A. But essentially, that's the changes I've made to this. But let's also have a look at find tile here. So this is the original find tile command, which this is mimicking. Now you can see we're not using the low byte of tile map anymore because it's over 0. We know it's over 0 because it's a requirement of the data structure, so we can forget about that. And you can see also, rather than doing rotate E and rotate D here, 2 0-page registers, we're keeping one of the 0-page registers in the accumulator because that's much faster. We still need to do the rotation of the L 0-page register, so we're effectively keeping half of these, but we've got rid of this D because that's much faster. I'll be honest, this original code is pretty lousy, really. I should have done it better. There's a lot of inefficiencies in Grime 6502, the original code, and Grime Z80, but I'm trying to do it quickly, so in some ways it's easier to have things simple and make them work well, rather than optimizing the crap out of things and being stuck debugging or scratching my head because my maths is so bad. So, but yes, that's what I've done there. And as I said, rather than doing add HLDE, there's no need. I know that E is going to be unchanged because the tile map's byte aligned, so why bother? So all I'm doing instead is just adding the H of the tile map here, and I'm calculating the offset version as well at the same time. So that's a lot easier. Now let's also look at simple tile. Now simple tile does various things, but the bit I was working on optimizing was the 6502 version. Again, I've done some optimizations. Rather than comparing Y to a value here, I'm now loading the value here and working backwards. That means less work. I'm no longer pushing DE because there was simply no need. I mean, really, this code now is doing the same as all of this code before. It was very, very inefficient. You know, I knew it was inefficient, but this original code has been designed to do a grid of, say, 48 by 48, which is my Chibico sprite on the example. Now it's only doing an 8 by 8 tile, so it doesn't need to move across anymore. It only needs to move down. So that's one of the reasons that the code is now much more efficient, is because it's just so much more simple. But another thing I'd like to show you as well is the screen pause command, because there was a sort of really clunky bit of code in here that I've managed to code out. Because if you look at this bit here, you'll see I was doing a loop around add DEBC here, and I've now coded that out into this rather crazy bit of code here. But effectively what this is doing is it's bit shifting the bits of the Y coordinate to be effectively the amount you would need to add. So this loop no longer exists. There's no loop at all, but this code is now instead creating a single value that will be the equivalent of the value that was being added here, and we just need to add it twice because of the configuration of the bits. But rather than jumping to an add command, I've actually unwrapped that and I've just put the code in here as well. So you can see now that this code here, while a bit longer than this version, is actually a lot faster, and that's saving some time. So that's another thing that I've done to optimize things. So generally everything's going reasonably well. There's some bugs, but nothing too bad. The time it took me to convert the code yesterday was very low, so hopefully I won't have too much trouble getting the rest of the logical code in. But obviously I do need to do more optimization, because while converting the code from Z80 to 6502 is very quick, the result is not very good. So more work needed there. And based on what I've seen here and here, I need to look at maybe my BBC code and some other bits of my C64 code just to make as many efficiency savings as I can, because at the end of the day I want to write good code so that when we use this code in the tutorials everything works nicely and efficiently. I don't want to be giving you code that's not the best I can make it. So there we go. Now, one other thing I'd just like to show you very quickly, just as a curiosity at this stage, is the Super Nintendo sound code. Because when you heard the Super Nintendo version, you probably thought, well, that sounded pretty lousy. I guess you'd be right, but I want to explain to you the utter pain that the Super Nintendo sound chip is to cope with. Now, this is Chibi Sound on the Super Nintendo, and if you've seen Chibi Sound before, you'll already notice it's about twice the size it usually is, but this isn't the thing that's doing most of the work for Chibi Sound. What is doing most of the work for Chibi Sound is this monster. Now, let me explain to you what this is. Now, the Super Nintendo, its sound chip is a separate processor, just like the Genesis, whereas the Genesis has a Z80 processor doing the sound and a 68000 processor doing the data, and also the Neo Geo does that. The Super Nintendo does the same. Unfortunately, the processor on the Super Nintendo is not a Z80 and it's not a 6502. It's an SPC 700, I think it's called. And nothing else uses it except the Super Nintendo. It uses its own programming language, its own instruction set, and it compiles to something that nothing else uses. So I actually had to emulate all of the commands that the Super Nintendo sound processor uses. You can see these are all macros to the correct bytecode. And then I had to write this, essentially this driver in this weird programming language that would wait and listen to the port that the Super Nintendo could talk to, receive the data, and then write it to the correct registers within the sound chip. It was a nightmare, it really was. But anyway, it sort of works. But I mean, the Super Nintendo sound isn't great, but honestly, the amount of work it took was not pleasant. So I'm just glad it's making any sound at all, to be honest. So there we go. So hopefully you'll join me next time when we do the next episode on day 5, because hopefully by then we'll be able to get pretty much all of the game logic working, and then I'll have some time to work on the bugs and the speed and all the other problems that'll probably come up by then. Anyway, thanks for watching today, and goodbye.